memory is the byte to write to. To demonstrate how an object writes multiple tiles to memory, suppose the working screen is screen number 0, and this object was determined to be placed at coordinates 5, 10. The tile index of the top left corner is pretty important, so let's call that the object's anchor point. In this case, we find the anchor point to be 16 times 10 plus 5, or tile index number 165. Screen number 0 is located at hex 6000 in memory, and then tile number 165 in hex would be A5, so the final memory address would be hex 6085. This is the memory address that holds the byte corresponding to this single background tile. That's for the top left corner tile. To get the tile 1 to the right, we just add 1 to the object's anchor point, 166. To get the tile 1 down, we just add 16 to the anchor point, 181. And the next would be 16 plus 1 more, 182. And so on for the rest of the tiles. However, this becomes a problem near the edges of the screen. Let's look at the horizontal case first. If this object had an X position of 15 instead, its anchor point would be 175. If we try to get one tile to the right by adding 1 just like before, we get an index of 176. However, that corresponds to this tile way over here on the left side of the screen. Therefore, if we want to build this object correctly, we have to perform a boundary check. If we add 1 to the tile index and we notice it wraps around like this, we just have to make sure to update the current working screen number. Well, actually we don't want to modify the working screen number since that's important for building the rest of the objects in the level, but we can make a copy of it and make note that we are now working on the screen one more than the working screen. This is an important distinction which we'll see the importance of in a bit. Anyway, now that we're looking at the next screen, we can write the tile here. Except we're still 1 tile too low, since wrapping around like that incremented the Y position by 1, so let's subtract 16 to counter that. It turns out that some objects properly wrap to the next screen like this, and some do not. We'll say that an object is horizontally smart if it performs the screen boundary check. An object that is not horizontally smart will just stay within the current screen, wrapping back around to X position 0 with an additional Y offset of 1. Now, what if this object had a width of not just 2 tiles, but 18 tiles? If it was horizontally dumb, it would just wrap around again and shift down by another tile. However, a horizontally smart object will stay stuck on the second screen. In other words, it would not advance to a third screen. Weird SMB2 code thing number 6. This is because of that distinction I made earlier. When it's determined that we must advance to the next screen, instead of incrementing the working screen, we make a copy of the working screen index and add 1 to that. So any subsequent screen boundary crossings will just repeat this process and end up on the same screen yet again, 1 after the working screen. This phenomenon actually comes to our rescue later since it essentially prevents objects from being infinitely long. They are constrained to 2 screens at most. Okay, that was the horizontal case. Now for the vertical case. Things are pretty similar here. Let's say this object had a Y position of 14. This would make the object's anchor point 229. Should we try to add 16 to get the tile below it, we would get tile index 245. Now, this is a problem. problem because screens only have 240 tiles, and this goes out of bounds into the non-existent 16th row. In this case, let's say we're in a vertical level. Again, we can perform a boundary check on our tile index. If we ever notice the index is greater than or equal to 240, we again make a copy of the working screen index and add 1 to it. This moves us to the next screen, and then to get to the top of that screen, we subtract 240 from the index. We can say that an object is vertically smart if it performs this boundary check. Similarly to horizontally smart objects, if an object is vertically smart, it is still restricted to 2 screens, so a very tall object will end up only extending over 2 screens maximum. What about vertically dumb objects? Well, they end up writing to that out of bounds index. Let's hold off on that for now and look at the next tile. This object was 3 blocks tall, so to write to the 3rd row, we add 16 to the index again. This gets us index 261. Except, remember that the NES's index registers are 8-bit, so they can't hold any values greater than 255. That means the index actually wraps around and becomes 5, which is the top of the screen. This is analogous to the horizontally wrapping that we saw before, except there is no additional horizontal shift here. It all stays in the same column. And notice that this screen only had 2 rows of tiles written to it. What happened to the middle row, the one stuck in limbo out of bounds? So, since each screen is only 240 bytes, this is sort of undefined behavior. However, in practice, like I mentioned before, all 10 screens of level data are contiguous in memory. So the phantom 16th row of tiles of any screen are shared with the top row of tiles of the next screen. This means that tile number 245 of screen 0 ends up being the same byte in memory as tile number 5 of screen number 1. In a horizontal level, this looks very odd since some tiles end up being modified they're pretty far away from the base object. In a vertical level, this just has the effect of looking like the object extends 1 block further down than you would expect. It doesn't break at the screen boundary, but rather 1 tile past it. All of this screen wrapping is important because it means only horizontally smart objects can be placed over horizontal screen boundaries, and vertically smart objects can be placed over vertical screen boundaries. Not all objects are smart, and for those that aren't, it really restricts where they can be placed in a level. Oh yeah, for our original example of this 2x3 object placed at the bottom right corner of the screen, let's see what would happen. If the object was completely dumb, we would get 1 tile in the bottom right corner, 1 in the top right corner, 2 in the top left corner, and 1 in the top corners of the following screen. If it were completely smart, it would wrap across and down to the next screen properly. But in theory, the last 2 tiles would still end up on the second screen, since remember, smart objects can only extend 1 extra screen forward. There are no objects in the game that are smart in both directions, by the way, so this case doesn't really count. These 2 tiles cross a horizontal and a vertical screen boundary, so without this restriction, they would have ended up on the third screen. A horizontally smart object would write the top 2 blocks straddling 2 screens at the bottom, and the bottom 2 blocks straddling 2 screens at the top. The middle 2 blocks would end up straddling the second and a third screen. This is an exception when the third screen comes into play. This is because these 2 tiles were written into the limbo out of bounds area of the first bytes long. Then the list of objects is terminated with a hex FF byte. Here's the format of the 4-byte level header. The most significant bit of the first byte signifies the orientation of the level. 0 if it's a vertical level, and 1 if it's a horizontal level. Bits 3, 4, and 5 make up the 3-bit palette index for this level's background. This can range from 0 to 7, but there are only 7 palettes defined, so setting this to 7 results in the color table being indexed backwards. Palette number 6 is also defined to be the subspace palette, so really there are 6 different palettes to choose from. Now, each of the 7 worlds has a different color palette table, so really only each world is limited to 6 different level palettes. This will become a theme, as you'll see, each world having different definitions for certain things. The least significant 2 bits determine the palette index for this level's sprites. This is a 2-bit value, so it can range from 0 to 3, but only 3 palettes are defined, so sprite palette number 3 results in included colors. These also vary per world, but are definitely not as varied as the background palettes. The lower 5 bits of the second header byte determine the initial floor pattern of the level. Like I mentioned before, this ranges from 0 to 31. However, pattern number 31 is undefined. These do not vary per world, but there are 2 lists of floor patterns, one for horizontal levels and one for vertical levels. Skipping to header byte number 4, bits 3, 4, and 5 determine the initial floor pattern blocks. The floor patterns are made up of 4 different kinds of blocks, but those blocks are not hardcoded. This 3-bit value can range from 0 to 7 and picks from a list of 8 different block combinations that can be used for the floor patterns. This means each of the 31 floor patterns has 8 block sets to choose from, for a total of up to 248 different possible combinations. Most of the floor patterns don't use all 3 block types, so this is an overestimate, but it's still very powerful and much less limiting than the floor patterns in Super Mario Bros. 1. And in fact, each world also has its own block set lists, so that's up to 248 floor patterns per world. And also, in fact, there are separate block set lists for horizontal and vertical levels, so really it's double that amount. The lower 2 bits of this header byte determine which music track will play in this room. The upper 4 bits of the third byte hold the length of this room on the screens. Being a 4-bit value, it can range anywhere from 0 to 15, indicating 1 to 16 screens, but since the maximum number of screens the game supports is 10, this should never be higher than 9. The last 4 bits of this byte have to do with what tiles certain level objects are made of. Bits 2 and 3 literally only affect how ladders look, so I'll bring this back up when I get to the ladder and vine mess. Spoiler, it's a weird SME2 code thing. Bits 0 and 1 determine which solid blocks will appear in the level, affecting objects 3 through 9. This 2-bit value can range from 0 to 3 and picks from a list of 4 combinations of blocks that this level can use for these objects. In practice, only objects 3, 4, and 8 have different options, but objects 5, 6, 7, and 9 have the ability to change as well. It's just that the table of tile numbers just has the same tile fill all 4 slots. And like before, each of the 7 worlds have their own lists, allowing for even more variety. Now for the object list. Most objects consist of 2 bytes. The first byte holds the position and offset of the anchor point of this object. The upper nibble has the 4-bit Y offset from the previous object, and the lower nibble has the 4-bit X position within the working screen. The X position can range from 0 to 15, since screens are 16 times wide, and the Y offset can range from 0 to 14, since screens are 15 times wide. The second byte, and potential third byte, is a parameter byte that defines the type of object, but it's used differently for different objects. Y offset 15 is unique. this weird SMB2 code thing number 7, since it's sort of awkward. Since the Y offset is used up by the special indicator, 15, and the X position is used up by the ID of these special objects, the offset within the working screen to change the floor pattern had to be encoded somewhere else. We need 4 bits to encode an offset